You know, space is just an incredibly hostile place, and the satellites we rely on every single day, they're constantly at risk. So how do you fix something on a machine that's zipping through orbit at thousands of miles an hour? Well, turns out you don't. You teach it to predict its own failures before they even happen. Let's dive into this really cool research paper that figures out how to do just that.
I mean, think about it. From the GPS that gets you to work to the global communications that connect us all, our whole modern world is basically built on this network of satellites. But these machines, they're getting hammered up there. Constant radiation, crazy temperature swings, and if just one little part fails, it's not a small problem. It can be catastrophic. We're talking a billion-dollar piece of tech turning into a hunk of dangerous space junk, just like that.
All right, so here's our game plan. First, we're going to look at the one specific part that's super risky. Then, we'll check out the old way versus the new way of dealing with failures. After that, we get to the star of the show, a really smart new fault detector. We'll see how it held up when things got tough, and finally, we'll talk about why this is such a big deal for the future of space.
Okay, first up, let's zoom right in on the one piece of hardware that's absolutely crucial for making sure a satellite is pointing where it needs to.
So it's called a reaction wheel. And the best way to think about it is like a figure skater spinning on the ice. You know how they pull their arms in to spin faster and stretch them out to slow down? A reaction wheel does basically the same thing for a satellite, just with a flywheel inside. You speed up the wheel, the satellite turns one way. Slow it down, it turns the other. It's a really clever way to aim cameras and antennas. But, and this is a big but, it's also a major weak spot.
And the stakes here, they're incredibly high. I mean, the researchers say it right in the paper, and I'm quoting here, they are prone to malfunction, which could lead to catastrophic failures. We're not talking about a little glitch. A failure here can send the whole satellite tumbling out of control, mission over. So that leaves us with the big question, what do you do about it?
All right, let's look at how engineers have tried to solve this, because this gets to a really fundamental problem they've been wrestling with for a long, long time.
So the old school way was pretty straightforward. Just pack a spare. It's called hardware redundancy. If one wheel breaks, you just switch to the backup. Simple, right? Well, the problem is, in space, weight is everything. Every single ounce costs a fortune to launch. So those backups are heavy, they're expensive, and they take up valuable space. But the new way? Oh, this is so much smarter. It's called analytical redundancy. Instead of packing extra parts, you use intelligent software. It's like having a tiny, weightless mechanic on board 24/7, just using the sensors that are already there to keep an eye on everything.
But that, right there, is the huge challenge. If you're going to rely on software, it has to be crazy fast and ridiculously accurate. It needs to see a problem starting, figure out what's going on, and do it all fast enough for the satellite to save itself before it starts spinning into oblivion. That's a tall order.
And this is where our researchers come in. With their brilliant solution, they came up with a new algorithm. Now, it has a bit of a mouthful of a name, so we're just going to call it by its acronym, CAUKF. And honestly, this is the real hero of our story.
Okay, so to really get what makes this CAUKF thing so special, you gotta first understand what it's built on, something called a Kalman filter. Now, a Kalman filter is this amazing piece of predictive math. The easiest way to think of it is like a super accurate weather forecast, but for machine parts. It's always doing three things. It predicts what a part should be doing, it measures what it's actually doing in reality, and then it corrects its own forecast based on the difference. It's just this constant loop. Predict, measure, correct.
So how does the new CAUKF's algorithm take that and just put it on steroids? Well, it follows these 5 steps. First, it predicts what the reaction wheel should be doing. Then, it measures what's really happening. Third, it compares the two. Now, if there's a big difference, it detects an anomaly. It knows something's wrong. But here's the magic trick, step 5. It adapts. This is the genius part. It's like a detective who finds a clue that just doesn't fit the story. Instead of throwing the clue out, the algorithm immediately gets skeptical. It changes its own assumptions to figure out what this new, weird behavior actually means. It learns on the fly.
So, it's a really clever idea on paper, but the big question is, does it actually work in the real world? Well, the researchers didn't just stop at the theory. Oh no, they basically threw every nasty failure they could think of at this algorithm to see if it would break.
And they came up with 4 really nasty scenarios. You've got your abrupt fault, that's when something just snaps instantly. A transient fault, which is like a temporary glitch that comes and goes. An intermittent fault, this one's a nightmare. It's irregular, on again, off again. And then the final boss, the incipient fault. This is the slow, creeping death of a component that gets worse and worse over time.
And this graph from the paper just says it all. Check this out. This is from that nasty intermittent fault test. That solid line? That's the truth. That's what's really happening to the part. Now, look at that dotted line. That's our new CAUKF algorithm. See how it just locks onto the truth and follows it perfectly, even with all those crazy jumps? Meanwhile, the other methods, those dashed lines, they're lagging, they're confused, they just can't keep up.
But the real, ultimate test was that incipient fault. This is what you'd call the silent killer for any complex machine. It's not a big, loud bang. It's a slow-motion failure. Think of a part just gradually wearing out over weeks. It's so sneaky that most systems would just write it off as background noise and miss it completely.
And look at this. Seriously, this is the money shot right here. That solid line shows that slow failure starting to creep in. Now look at the other lines. Those are the older algorithms. See how they're just all over the place? They're wobbling, they're lagging, they have no idea what's really going on. But then, look at our CAUKF line. It sees that slow failure and tracks it almost perfectly. It proves it can spot even the quietest, most dangerous problems out there.
So what's the big takeaway here? What does all this mean? Well, this isn't just some abstract academic paper. This is a breakthrough that could completely change how we operate in space.
Let's boil it down to one number. When it came to spotting that super difficult slow-creeping fault, this new method wasn't just a little bit better, it was up to 10 times more accurate. 10 times. That's not an improvement, that is a gigantic leap forward. And here's the data that backs it up. This table shows something called mean squared error. You can just think of that as a wrongness score. The lower the number, the better. And just look at the score for our proposed CAUKF. It's not just smaller, it's a whole order of magnitude smaller. That is a night and day difference.
So what's the payoff in the real world? Well, for starters, you get much more reliable, truly fail-safe satellites. It also opens the door for smaller, more capable satellites that just can't carry heavy backup parts. This is a massive step towards having truly autonomous systems up there that can look after themselves. And maybe most importantly, by stopping these catastrophic failures before they happen, we can help reduce the amount of dangerous space junk floating around.
And that really leaves us with one last big thought. Okay, so this paper is about satellites, right? But the idea behind it is universal. I mean, if we can teach a machine, flying through the vacuum of space, to diagnose its own slow-motion failures with this kind of intelligence, what else could we make fail-safe? Our power grids? Self-driving cars? Crucial medical equipment? The possibilities? They're just staggering to think of.